Morning, everyone. I'm Dr. Amini, and I guess most of you guys know me. And today I'm going to talk about part of our research, one thrust of our research that we do at our research lab. So I guess you guys are all ready, huh? Ready for sleeping? Okay. But never mind, I have this bottle of water. It's not just for my drinking, it's for whoever who sleeps. So I will use this one, okay? All right, so let us start. My talk today, as I said, is about Edge+Systems. So, sorry, AI+Systems. I've said Edge so many times that I even read AI as Edge. So AI+Systems is basically what I'm going to talk about, and that is about AI, as you guys all know about, the most fancy term these days, right? But probably not from the perspective that all of you or most of you are involved in the training and layers and this and that. It's more from the systems perspective, okay? And I will tell you what that means in a few minutes. All right, but first I want to, this is basically the outline of my talk. I will first introduce myself. I haven't done it yet. Then I'll talk about our research vision and mission and scope of our research, what we are doing. And then we are, the main thing, the core of this talk is about the strategies to bridge the gap between machine learning and systems, right? Because we believe that there is a gap, and we want to bridge that, overcome that gap, so that the ML systems become usable. And I can tell you the solution very quickly that we have. The solution is that ML systems or AI-based algorithms have to be co-designed with system solutions. So AI algorithm plus system software co-design is what we believe should happen. That's what we advocate in this talk. Okay, a little bit of myself and my group. Again, I'm Dr. Mohsen Amini. I've been here since 2014. So it's my 9th year here. And I'm an associate professor. I direct the HPCC lab, High Performance Cloud Computing Lab. You can see some of our team members here. And yeah, so we have several, I guess 6 PhD students plus some undergrad students and 1 master's student who is going to work with us. And then over the years, we have had several other students and postdocs and visitors from different places. So, so basically our vision, this part probably is repetitive for the ones who attend my talk last semester, but many of you are new. So how many of you are new, basically? This is your first semester. Yeah, maybe around 10-ish. So I have to repeat this part, and I guess it's an interesting part. So it doesn't hurt if I repeat that. So so the vision that we have in our research lab is that the past decade, there are some seats here. You can sit over here as well. So the past decade, let's say from 2010-ish to 2020-ish, and these are all approximate, right? We can call the past decade as communication everywhere. So in the past decade, people were excited by having access to Wi-Fi everywhere, right? Or any type of wireless communication, right? So basically, the idea was that you enter the university or a grocery store, a shopping mall, whatever place, and then they offer you free Wi-Fi. That was so exciting, right? Before that, we didn't have such thing. It was like a dream if you can connect to the internet, everywhere wirelessly. And so over the past decade, all of us remember different generations of mobile communication that help a lot in this communication everywhere emerge, like 2G, and then people were excited about 3G, 5G has been, discussed for several years, and now it's out. And I mean, out means like in the market. And of course, several other wireless technologies, 802.11 protocols, Wi-Fi, and all that came to play, and eventually it happened. So nowadays we have communication, which means networking everywhere, to the extent that we are sick of it. We look for places that do not let communication happen, right? For example, some restaurants, I've seen that they put signs that, okay, Wi-Fi is not available, or you cannot use your phone here, and things like that. But put that aside, this communication everywhere has changed our life dramatically, right? I guess all of us agree on that, this emergence of smartphones, along with this communication everywhere, that were hand in hand actually, was a paradigm shift in our lives. So the way we live nowadays is different with 10 years ago, 15 years ago, significantly. But then this wave is going on, it's not stopping, and we are in the current decade, we are actually moving to a new era that I call it computation everywhere, or computing everywhere. With that, I want to say that people are not excited with having, network access everywhere. That's become, banal. It's like, okay, so what? So now what people are excited about is actually having computing everywhere. So basically, I mean, there are many examples of it. Like you go in your car and it has a lot of new apps and applications that can help you, even self-driving cars. Even without self-driving cars, these modern cars have a lot of gadgets that help us, and most of them are somehow network-based. They connect to your phone, they connect to internet, all these type of facilities. They even charge you for some of the facilities that they provide to you, which means that that's also network enabled, and they do some sort of monitoring what you are doing, and you can turn on some features and pay monthly and things like that. So so that is what is happening nowadays, computing everywhere. And this computing everywhere has been along with a lot of gadgets, right? So from the appliances, your refrigerator, washing machines, all those things are kind of compute enabled, and they are connected to the internet, what is so-called IoT, right? Cameras, smartwatches, drones, you name it. There are like smart cars. So people are so excited about it, and they mostly think that it is these devices that provide us this smartness, right? But that is not the right impression. This is only the facade, not only the facade, but that's the last layer. Behind the scene, there is a lot going on. There is a hierarchy of computing happening, that this cooperation between these compute layers, in fact, provide us the services, right? So for example, when you use drones, or let's say even not drones, like your phone, a more evident example, most of the apps that you have on your phone, they don't do much on your phone. They are mostly doing something on the cloud, right? Let's say if you use for podcasts, right? If you use YouTube, if you use Amazon for shopping. So they have the interface, of course, on your phone, but behind the scene, most of the things are happening there. Even things like Siri or other apps, they're all cloud-based. They all use these backend compute devices, compute services. And if you really disable the communication of your mobile phone, there is not much of use for it, except for the flashlight, right? And calculator probably. But others are somehow depending on these computing tiers. Now, so we define ourselves within this scope of practice and research. So how to provision this computing backend for the modern services? So basically, we define our research to devise compute systems that improve the quality of life of human beings, right? So we want to basically innovate in this computing across this computing system to make the life of people easier and better. So along that line, we have several trusts of research in our group. There are some seats over here for the newcomers. So, on one side, I mean, one of the main tracks of our research that I'm going to talk more about today is basically developing systems, and I emphasize on the word systems. So what we do in our research is designing systems. And that may not make sense for you, but it essentially means that everything that relates to computers, like basically deploying the applications on the computers, on the computing tiers, better to say. So we are not doing application development specifically, but we rather deploy that efficiently across different layers of or different tiers of computing systems. So that's why I'm saying developing systems to make production AI application usable. So this is also important, and specifically for disabled people. And the reason that we target disabled people is that, you know, the mainstream industry doesn't care enough, doesn't pay enough attention to these type of people, just because there is not a huge market. Yes. Sure. I mean, I thought it's evident, but it seems it's not, because it's in our group it's evident, but not probably for everyone. So basically, fog is, we can say, a mini cloud, right? So let's say in analogy with network, right? Just analogy. So suppose that this is internet, and then when we have internet worldwide, but in our campus we have a gateway, right? That manages the network internally. You can, in analogy, you can put this one like that gateway. Institutional cloud, right? That also can give us some domain-specific services. Whereas that one is global, like Amazon Cloud and Azure Cloud and others. Thank you for your question. I didn't think that I need to explain it, but I suddenly remembered that this is a more like broader audience, so I need to explain more details. So, so what we do is developing systems to make AI applications usable. So AI applications, everyone is doing very interesting. I mean, it's changing our lives definitely. But what we envisage is that those solutions are not practically usable in the production scale. So, for example, there are all these, AI-based applications for face detection or for, object detection, motion detection, different types of applications. But the problem is that, just one problem is that they drain a lot of battery of your device. So if you keep using them, your battery will be drained in 1 hour, right? That is the problem. We don't, I mean, probably in a day-to-day life, you don't realize that, but once you travel, once you go somewhere with not, constant access to energy sources, then you will see that how much a problem that is, right? You need to charge your, let's say, mobile phone over and over, right? So we want to make that happen. We want to make that, let's say, your mobile phone can endure for 1 day at least, right? Instead of 1 hour or a couple of hours, right? So that is the usability aspect. We want to make it usable. And specifically for disabled people, for the reason that I mentioned. And then we have a project on that specifically tries to help blind and visually impaired people using a continuum of computing tiers. so that instead of they use the white cane, they just wear a smart glass and they have the life like a normal citizen. They can do all their day-to-day activities. Basically, that smart glass gives them the perception of the environment. Okay, so that's the idea. So another thrust of my research that I'm not going to talk about, just to introduce, our research agenda, is on the cloud side. So this is more across edge to cloud. This is more on the cloud side. This is more on next generation cloud systems, how they're gonna be. They will be domain specific, they will be easy to use, and things like that. So we try to enable cloud systems that anyone, literally anyone, can program them. Nowadays, cloud is there, very useful, but just some people can use it. I mean, everyone can use it, but some people, only few, not few, just some people can develop program in it. So it's an expertise to work with cloud. So we want to break that. We want to make everyone able to program clouds. So that is another track of my research that 2 or 3 of my students are actively working on. And then we have a third track of research that is more helping the environment, like how cloud and edge computing systems can help to preserve the environment. For example, in doing things like oil spill detection in the middle of the ocean, where we have a lot of oil fields, and if we utilize edge and cloud computing technology effectively, we can prevent or cope with these disasters in a much more efficient way. But don't worry, I'm not going to talk about all of these. I'm just going to introduce the first one. So this is the scope of the research that we have. And last semester, I talked about the left side, the domain-specific serverless clouds. And this semester, I'm going to talk about this part. About our project, which is called SmartSight, that aims at providing ambient perception for blind and visually impaired people. So I guess this is slide. This is an important slide, but I already talked about it a little bit. The thing is that the idea of this project and this work is that ML systems, machine learning systems, or applications, I shouldn't say systems, machine learning applications and systems have been developed independent from each other, right? So the scientists who are working on machine learning, generally, they don't pay attention to the system constraints. They just want to, make it more accurate, play with these active functions and the weights and all those things so that they can do a better job. They ignore the system side. System side also try to design systems that are more generic, right? That can support anything. So they don't make, nowadays they do, but generally they don't make domain-specific circuits, right? So they want to be as general as they can. So that's why they are orthogonal to each other. Each one goes its own path. So they are orthogonal to each other, and that's why they don't match each other well. That's what we want to do here. We want to match them together. We want to make sure that they operate together well, so that the ML applications are usable. Again, I emphasize on this usable across this compute systems. And the context, as I said, is this blind person who uses a smart glass, paired with the edge system, something like your mobile phone, and then with fog and cloud, and collectively they can do their day-to-day activities, like, for example, shopping and identifying what is the object, what is the price, what is the ingredients, like whatever we can do as a sighted person, they can do it as well. And this is the area of, our main approach is ML algorithm plus software system co-design. So this co-design is the keyword here. They have to be designed together, not orthogonal, not independent from each other. And that's where the problem arises. Okay, so I keep emphasizing on the word usability, right? But I didn't mention much. What is that usability? I did mention a little bit, but not much. So for an ML application to be usable, what features should it have? I mean, there are several things, but we can name at least 4 things. Latency, right? These AI scientists working day and night on making it more like faster and faster and faster. Great job, great achievements. However, because they don't think of the system aspect, whenever it comes to the system aspect, we see that all the things that they have done to reduce the latency for 1 millisecond, is not satisfying, it's not satisfactory, it's not doing what it intends to do, because in systems we have some factors that imposes overheads at the level of seconds. So you have improved it at the millisecond and you are very proud of it, but in practice there are some hurdles, there are some obstacles that gives us a lot more latency. So that's the one usability aspect. The other one is that this ML applications are very resource intensive. I guess everyone agrees with that. So they need a lot of resources. And now that's fine. I mean, we have big servers, we can deploy it on them. But the problem is that in many use cases, we have to deploy them on edge devices, on tiny devices, let's say your phones. Or battery operated devices, right? So that's the resource intensiveness becomes very challenging in that situation, specifically when it comes to reality, to systems again, because systems are very real, right? So we use them in a day-to-day basis. You have multiple of these applications together, so they are kind of concurrently running. So let's say that blind person that uses that smart glass and all that gears. So the system has face detection to detect the face of people around the blind person, obstacle detection, right, to prevent obstacles, motion detection to detect the approaching objects, right? A car is approaching or the door is approaching to the face of the blind person. So those must be detected. And the thing is that each one of them is heavy, and they have to be done concurrently and continuously. It's not like Siri that you say, hello, Siri, and then bye, that done. No, it is concurrently there. Like our eyes that are like permanently there, right? Unless we are sleeping. So that thing, so resource intensiveness is a big issue, specifically when it becomes concurrent, when it becomes what we call it more technically multi-tenant. So on your mobile phone, not even having one AI-based application, but multiple of them. I'm sure your mobile phone cannot sustain for more than maybe a few minutes or at most an hour or so. So accuracy. So that's another challenge. That is, I guess, we all know that we want the things that are more accurate. So why I'm not AI guy per se, but why I'm bringing it up here, because sometimes we need to compromise the accuracy because of system challenges, right? So for example, to address the resource intensiveness of the things, we need to bring down the quality, the accuracy. And that's what I was saying, that AI people, work day and night to make it a little bit more accurate. And then we say that, okay, we cannot do it. So go to the lower level of accuracy. So that is the thing. And then fourth usability problem or challenge is energy. Edge devices are mostly, not always, battery operated. And then I guess all of us have experienced, being in a far place and our mobile phone or our edge device, what we call it, is running out of battery. And, just imagine that you are traveling somewhere that you don't know anyone or anywhere, no address, nothing. and then you get stuck in the middle of nowhere without your mobile phone, right? Or without your Edge or PDA, whatever you want to call it. All right, so these are the challenges that we have for usability, and I listed 4. You may mention more items, but I'm going to mention some of these problems more deeply and the solutions that we have for each one. All right, so let's start with the first one, latency. We want to dive deeper into this aspect. So, so I said that, and I guess I will repeat that a few more times until the end of this presentation, that we have that AI people working day and night to make the latency, lower and lower, making it faster and faster. Great. But the problem is that once you give it to us, means system people, and we deploy it, we have some problems, we have some hurdles that makes the latency much higher than what they were trying to do. What is the issue? The issue is that when you want to deploy ML applications on edge, cloud, any kind of deployment environment, that's what we call it, deployment in practice. The application, the program, right? What you guys call it program. The program is not running like, okay, this is Python program, Python dot, main.py run. It's not like that. We containerize it. We put it in some package, right? We put it in some packaging known as what? Known as virtualization. Known as virtualization, but virtualization is a broad term. We have different ways to virtualize things, right? And you can see here a list of some of them. So you can do it on bare metal, which is not very common. You can containerize it. I'm sure some of you or many of you have heard of Docker or Podman or other technologies like that. So this is the containerized. That's one way to package your application. And why we do package it? Because it's easier to maintain, because it doesn't interfere with your with other applications in your system. There are a lot of benefits for these things, for this virtualization in general, but it can be in different forms, in forms of containerization, or it can be in form of a unique kernel. This is a newer technology. I'm not going to spend much time on it. And then there are other ways like micro VMs, virtual machines, very popular, very, very popular. Cloud became cloud with these virtual machines. So for those of you who were following cloud computing since like 2007-8, virtual machine is one of the main pillars, right, of cloud. So everything there is virtualized. Okay, so, and then we have even more complicated things. We have containers inside virtual machines, right? And you know what? This is the most common approach for deployment, which looks very convoluted, right? You have a virtual machine. Inside that, you have a container. Inside that, you have your application. Now, what is wrong? What's the problem with this? The problem is that these guys all impose overhead. They impose overhead. They are not free of charge, right? So basically, your application, these are the layers of overhead that your application should go through before being executed on the hardware. This is the hardware. This is the layers. So in this case, let's say 1, 2, 3, 4, 5 layers of overhead. That is why I was mentioning that, that 1 millisecond will not help us, because these guys sometimes impose overheads in the order of seconds. Now, I wish that was the only problem. That the problem is broader than that. The problem is that we have different virtualization techniques. Each one of these techniques have different overheads. And then that I already mentioned. And then as a person, what we call it, cloud solution architect, right? That's the technical term a little bit. But as a yes, sir.
Yeah, so if the latency is so high with container and virtual machine, why is it commonplace?
Then I would suggest you to take are you undergrad or graduate student? Okay, then take CMPS 432, I'll spend the whole semester to explain that to you. So the thing is isolation, right? Isolation. The best way I can explain it to you is shipping, right? Shipping. In shipping, let's say shipping like 100 years ago. How was that? Of course, there were ships and like cargo ships, and they were putting items next to each other, right? And it was very likely to put, let's say, salt next to a barrel of water or oil, right? Then what happens is that the oil or the water may penetrate into salt. And by the time you reach destination, you know, you have to respond to the owners of those shipments. So now find the connection with cloud computing. Yeah. So the connection is that, now let me ask you this question. How is the shipping these days? How do they do that to prevent this type of leakages?
They usually have like designated ships that.
Yes, that is fine. Those ships were also designated, but nowadays they use containers. Have you seen that, you know, things, you know, that very nicely and organized? They put it. Why? Because of this issue. The same, exactly same issue we have in clouds. In clouds, you have your application, someone else has his own application, her own application altogether. You cannot leave them unprotected. You have to protect them. We need isolation from each other. That's what the purpose of these virtualization techniques are. And there is a lot of details behind that, but that's the quickest way I could explain to you. Any other question? All right, so moving on. So then this cloud solution architect has this question. Now I am given an AI-based application. How to deploy that? Which item I should use? Which type of virtualization I should use for the deployment? What is the overhead of each one? Well, someone may say that choose the one with the lowest number of layers. In this case, what we call it CN or containerized. Evident, right? So why is it a challenge? We will see. So, I mean, if the question was only this one, it was not a big deal. I could try an error and find the best one. But the problem is much broader than that. First of all, we know that when we talk about deep learning and machine learning, we have both training and inference. I have a good news for you that we are not talking about training at all. We are talking about inference, because I'm talking about day-to-day activities. In day-to-day activities, you don't do training, you do inference. And I know, I guess you know what inference is. And then the other dimension is that when it comes to deployment, I have the choice of GPUs. Should I deploy them on GPUs or CPUs only? AI applications. And when it comes to CPU, would it be x86 or ARM? You know, so you can see that the decision space is growing. And then when you choose your, you choose all these dimensions, then there is all these types of different containerized systems or virtual machine or containerized VM and all those things. So there's already another dimensions that you need to consider on the hardware side. So there is another thing on the software side. There are some more degrees of freedom on the software side, on the application side. For that, I need to teach you a little bit of AI stuff. So this is the internal structure of inference. So when you do a machine learning inference, what happens? So in inference, this is a very popular picture nowadays. So we have a cat and we want to recognize that. So this is an inference operation. Within inference, this source image is first need to be converted to what is so-called feature vector, the bunch of numbers, right? Bunch of numbers that is understandable by what? By your neural network. So at the heart of your machine learning application is a neural network. DNN, deep neural network, right? But before that, we have this pre-processing. And after that, we have post-processing. to tell us, was it cat, was it dog, was it what, right? So but be aware that each one of these is a separate module and has its own overhead. So does this structure that people generally ignore have some impact on my deployment? You'll see yes. You'll see yes, it will. And then considering all this background that I provided, the question that we need to answer is that basically how to choose the destination, the deployment plan, basically. There are a lot of things to talk about, but I summarize them in a few questions. Which platform? Basically, if it is gonna be on cloud or on edge, because they have different characteristics. Which type of compute unit? Second question. Is it gonna be on GPU or CPU only? That's another thing. And then there are more things to discuss. Like, for example, when you use CPU, you can pin your CPUs, which means that the application only sits on certain cores and it doesn't move within your CPU. So that's one dimension. And then another dimension, and also, should I use GPU or not? Should I use CPU in a pinned or unpinned version or configuration? And then the other dimension is that is the scale up. For those of you who have familiarity with cloud, you know that when you want to create a virtual machine in cloud, you can create it with 2 cores, with 4 cores, with 8 cores, with 16 cores, with 32 cores, with 64 cores. And I guess 64 is the maximum we have tried, but I guess 128 is also possible. We haven't tried though. So this is another dimension there. How big of a virtual machine should I create? How big of a virtualized environment should I get? So what you can see that there's like a wide variety of options to check. To control that variety of options, we have conducted an extensive search, if you will, across all different cases. So here I can just, because, for the sake of presentation, I just show the cloud use case. We have a similar use case for Edge, which is Raspberry Pi in our case. But we use just for cloud. Here I show just for cloud. For cloud, we use different virtualized environments. I already introduced them. For each virtualized environment, we use we examine different applications because each application has its own nature, right? Each application has like image detection. Object detection has its own nature. Speech recognition has its own nature. All these different types have their own characteristics. So I want to see the impact of image classification, speech recognition, NLP type applications, recommendation system. They have different internal mechanics. And then each one of these, we want to see on different types of machines. That I also explained. Like CPU, just normal CPU-based machines. Pinned CPU, which means that the task on the CPU cannot move around, right? And then GPU plus CPU, of course, but the CPU is not pinned. GPU plus pinned with CPU. And that's the third dimension, the fourth dimension. And the fifth dimension is the scale up. And for those of you who do not know what is a scale up, it means that how many cores your virtual machine would have. 4 cores, 8 cores, 16 cores, 32 cores, 64 cores. So we examine all these cases. And it was honestly very difficult to grasp what is going on in this wild graph of cases. So, going a little bit deeper about the experimental study that we have done, we chose different applications. I guess I explained that. We use the commonly used one, the ones that are related to the user, not the ones that are in the backend necessarily, and they have different input types. And we used in different domains like vision, speech, language, and of course on edge as well. So I skip these things. These are the characteristics of the applications. I will skip them. This is the characteristics of the machines, which I said x86 and ARM, and then different virtualization. We call them execution platforms, just not to be confused with virtual machines. Essentially means virtualization, like bare metal virtual machines, micro virtual machine, and containers within virtual machines. So these are the setup that we have. And this is the result of some of our analysis. So the figures look a little bit hectic, but I try to unfold them so that you understand it better. So first, these two figures show two main scenarios. Only CPU-based system, no GPU, and CPU plus GPU. Okay, so let's focus on this one. Each one of these show a different execution platform, is a virtualization technique. Just virtual machine pinned, just containers pinned, vanilla VMCN, which means VMCN unpinned and VMCN pinned. VMCN means container as VM, and bare metal, nothing, no virtualization. Why do I do that? Because the whole thing, if you remember, was to measure the overhead. So the main question is that what if I have virtualization? How much more burden does it impose or I should tolerate because of the virtualization? So that is like the benchmark. We compare others against this one. Is that making sense? Okay. So, and the similar thing happens on the other side. So similar thing, similar approach. And then within each one, now we focus one level deeper. On each one, we have for 4 cores, 8 cores, 16, 32, and 64. Do you remember that scale-up dimension? That's how we address it. Okay, so moving on, let's see what we learned from these graphs. So the thing that we quickly learn is that by increasing, this pattern has repeated. So by increasing the number of cores, expectedly, the average inference time has reduced. You know, it's expected. However, we can see that the improvement sometimes is insignificant, right? So, and be careful that here we have 32 versus 64. So the message is that beyond some certain point, you don't get any speed up. Don't waste your money on the cloud just because you have money I want to spend. No, don't do that. It doesn't give you any benefit, as you can see. Exactly. That is exactly what is so-called Amdahl's law. It's proven in CMPS 432 or CSCE 533. We show that this. We tried that. We examined that in an assignment. But anyway, you can see the Amdahl's law here. Now, do you recall that picture that I showed with different virtualization techniques like containers, VMs, and different numbered layers like 1, 2, 3, 1, 2, 3, 4, 5? And do you remember that I said that containers with only 1, 2, 3 has the lowest overhead? Now, here it is, the opposite. Containers actually have unbelievably long overhead, 160 seconds if you choose them to be very, very small, like 4 cores. And then when you increase the number of cores, they become like others. This is counterintuitive, right? We expected this one to has the lowest overhead and is like the worst overhead. So if you ask people right off the bat, they would say that use containers, they're very low overhead. They are not. It depends. They can have, but it depends. And one more thing, they are not too wrong, because if you pin your CM, your container, you can right away see that containers, if they are pinned, they have the lowest overhead. So the problem is pinning. So if you don't pin it, which means that your container can move around within the CPU wherever it wants, the overhead goes high. Why? We digged into it, and we realized that for this container, OS has some modules that should keep track of this one, right? Where is it going? Is it encroaching to other spaces? Yes, no, but this monitoring has overhead. And the larger the ratio of your container cores to the total number of cores, or the larger the container is, the larger your CPU is, this overhead is more. Because there are more options that this container can move around, and this guy can chase it to make sure it's not going beyond its quota, right? So that is why you can see when the number of cores are so low, because the number of options that it can move around is a lot. We have seen this strange behavior. But once you pin it, that is not going anywhere. So the overhead of chasing it is much lower. So if you want to use containers, pin it for this type of applications at least. Now, another surprising thing that we noticed was that if you ask people, say that I want the AI application, say, oh man, you should use GPU, right? That's, you will hear from 99% of people. And that 1% is us saying that no, not necessarily. Because what we see is that with GPU, in fact, the overhead does not reduce much for this application. It very much depends on your application. So the lesson that I want to tell you is that try your application before deploy that. Find out its characteristics. So what does this application have? And by the way, this is image classification application. So why it is this? Why it has this strange behavior? And the behavior is stranger because when we see that by increasing the number of cores, the performance gets worse, right? So you give it more cores and the performance goes down. Unlike here, that at least it gets flat, but here it goes up. So what is going wrong here? The thing is that when you have CPU, GPU, the data must be copied back and forth between CPU and GPU, right? Now you have more cores. Therefore, you have more concurrent inference going on. Therefore, there are more programs that are trying to copy their data back and forth. So the GPU itself becomes a bottleneck, right? And the bigger your CPU is, because you know that GPU is connected with CPU, right? We don't have GPU alone. GPU is always connected to CPU. So the bigger your CPU part is, the more concurrent tasks are running. Therefore, the more competition, the more contention happens for the GPU. Therefore, the overhead goes high, as opposed to, unexpectedly, because we expect the opposite would happen. So, and then there is some more stuff going on, like the pre and post processing part. Yeah, so let me explain that one too. I was thinking if I can skip it or not. So there is another factor. The other factor is that end-to-end thing. Do you remember that pre-processing, inference, post-processing? That pre and post-processing, like whatever GPU is only useful for that neural network part, for that engine. How about the pre and post-processing part? Sometimes they are heavy. Sometimes they do some significant things. Sometimes their execution time is considerable. So, and they are not GPU enabled. They are a bunch of sequential codes. They cannot be done on GPU. Or they are not done, at least at this point of time. Maybe in future someone will do that. So that also contributes to the problem. So these pre and post processing are on CPU, the core engine is on GPU. So that makes the problem even worse. Okay, so I guess I shared this lesson that scrutinize your resource utilization before spending on the cloud. know the pattern of your application. Investigate the impact of speed up. I guess I talked about this one too. All right, so the next thing that we want to mention is that we want to basically explore more the impact of those pre and post processing, right? Specifically, because we were surprised by this behavior in GPUs that the execution time goes upper instead of going down, we eliminated the virtualization factor, right? So we concentrated on both bare metal cases because we want to reduce the degree of freedom, right? Just focusing on the bare metal case. And then for each case, we measure the pre and post processing time and the inference time. Okay, so the thing is that we realize that when we use GPU, let's say 4 cores, right? 4 cores. So when we use GPU, the post-processing time and pre-processing time has remained the same because they are CPU-based. They are not GPU-enabled. But the GPU part has gone down from 15 to 4, which is expected. But the problem is that when we use GPU in that case, see, the time of pre-processing dominates the time of the inference. So you are trying to squeeze the time of inference, but the problem is somewhere else, is in the pre-processing, right? So that is what we realized, that the time of pre and post processing may even dominate your execution time, and from that point, whatever more you spend, whatever bigger instances you create, it doesn't help, and it may make things even worse. Why? Because of the contention that I mentioned earlier. Because you want to make it better, you give it more CPU cores, and the more CPU cores create more contention for the GPU, create more interrupts, create more context switches, and end up the system being trashed, right? So that's what you can see here. Okay, so I guess I'm going beyond my time, and you will be surprised how many more slides I have prepared for today. So I couldn't even finish the first part. So let me skip this part. Okay, sorry, I guess I have to skip. So this is for other types of applications that I compared them, like for different application types. This is for for the Edge, and I have some good news here that for Edge we don't have all these variations possible because for example, they don't have pinning because it's so tiny. What do you want to pin? Right? Pinning makes sense on a larger scale. So the good news is that, and we tested for 2 applications, the container is good enough for Edge. And then that's the first part. And imagine I have 3 parts left. But don't worry, I'm not gonna explain them in half an hour, in 5 minutes, sorry. But yeah, so the next thing is that now it is good on Edge, at least it's good to use containers, right? But then there are some circumstances that your Edge becomes oversubscribed, your Edge becomes too busy, right? So there are many use cases. For example, one use case is that we have this scenario all the time discussing that, let's say in a coffee shop that has some Edge, some servers, basically. Some people are, doing some gaming, online gaming, and then so gaming is not a very high priority thing for that coffee shop to take care of, specifically when we have some more high priority user coming in, right? So in this situation, the Edge is being oversubscribed. So what to do? The only way we can think of, not the only way, one way we can think of is to migrate, live migrate, because they are playing I cannot say stop playing, I want to migrate, right? That's awkward. So we want to live migrate the service to the cloud, and then the opposite would happen when the person leaves the space, like the blind person. And this is very common. Like for example, in like in a shopping mall, we have parking lots specific for disabled people, right? So soon, I expect we will have, like in shopping malls, servers, and they have to provide servers, or they will have to provide servers just for disabled people. And they can be used by others, right? So the same way we have dedicated parking for disabled people in a parking lot, right? Similar idea, but in a dynamic manner. So you can use the server unless there is a disabled person who wants to use it. So something like that, and this will be used in that context. I know that I'm going beyond our time, so I open myself for questions if there is any.